Determining an equation that describes the behavior of a set of data is an important tool for engineers and scientists. For example, we can measure the elasticity of a material at a variety of temperatures. The individual data points that we measure, however, aren't normally useful for design. You need a mathematical representation or a model of the data's underlying behavior. One way to get this model is to create a line that you feel best describes the data. There are a variety of ways to define best. This tutorial will demonstrate how to use Matlab to implement one of the most common ways to do this, which is a least squares fit of polynomials to a set of data. Now, before I get into the specifics of curve fitting, I'll talk about how Matlab represents polynomials and give a brief list of some of Matlab's polynomial-related functions. I'll also do a brief and very non-mathematical description of curve fitting, or as it's also called, linear regression. I'll end this video by talking specifically about using Matlab to fit polynomials to some data and then demonstrating the process using Matlab's Polyfit function. Matlab makes it really easy to represent polynomials. You just put the polynomial coefficients in a row vector. The coefficients are placed in the vector in descending order of the power of the independent variable. As an example, consider this polynomial. If we want to represent this polynomial in Matlab as a variable named, say, y underscore coef, we assign a variable name, y underscore coef, an assignment operator, an open square bracket to denote that we're creating an array, and then the coefficients in this polynomial. We have 3 times x to the 4th minus 5 times x cubed, nothing times x squared, there's no x squared term in here, 1 times x, and negative 4 times x to the 0th. So our highest order coefficient is x to the 4th. Then this multiplies x cubed, 0 multiplies x squared, 1 multiplies x to the 1st, and negative 4 multiplies x to the 0th. Matlab has several functions that are intended for use with polynomials. Polyint and polydir will integrate and differentiate polynomials. CONV takes the product between two polynomials, and DE-CONV is used to divide two polynomials. You can find roots of polynomials with the roots command, and polyval can be used to evaluate polynomials at specific points. Finally, polyfit is used to perform least squares curve fitting of polynomials to data sets. The polyfit command will be the main topic of this tutorial, but we'll also use the polyval function when we get around to plotting the curve fit. Now I'll cover the general idea of linear regression or curve fitting. I'm not going to get into the mathematical details. Since this is a Matlab tutorial, I just want to give you a basic idea of the process. If you're interested in the mathematics, there are plenty of resources available. An internet search on linear regression or least squares will provide you with plenty of information. The fundamental idea is that I start out with a set of xy data points. I want to approximate this data as best I can by a straight line. The equation of a straight line is y is equal to m times x plus b. The slope of the line is m, the rise over the run, and the y-intercept of the line, where the line crosses the y-axis, is b. There are lots of ways in which you can choose a line that you think represents the data. One of the most common is what's called a least squares best fit. That means that we take the vertical distances between the data points and the line, we square those distances so that we always get a positive number, we add up all the squares of those distances, and then we minimize that sum. As I already mentioned, Polyfit performs least squares curve fitting of a polynomial to a set of xy data points. This is the general syntax of the Polyfit command. The first two arguments, x and y, sent to the command are vectors or one-dimensional arrays containing the x data points and the y data points in that order. The third argument is a number, n, which provides the order of the polynomial that would be fit to the data. So if you set n equal to 2, you'll get back a second order or quadratic polynomial. The Polyfit command returns a vector containing the coefficients of the best fit polynomial. These coefficients adhere to the rules for polynomial coefficients that I already gave you. Now let's do a demo of using this function. I've already defined some data in the workspace, since there's nothing more boring than watching someone type in numbers. Before I do anything else, I'm going to plot the data. Always examine your data before you jump in and start fitting curves to it. Any analysis you do needs to make sense in terms of the data itself, and that is usually a subjective decision made by the engineer doing the analysis. Anyway, I'll plot the data as red circles by typing plot of x, comma, y, comma, quote, r for red, lowercase o for circles, end quote, close parentheses. Notice that I haven't put a line on the plot of the data itself. We shouldn't add a line here, since we have no idea how the data would behave between these points. We don't have any information other than that given by these pairs of xy points. Now I'll fit a straight line to the data. A straight line is a first-order polynomial, so the syntax for our command will be coefs underscore 1, which will be the variable name where I store my coefficients, equals polyfit of x, comma, y, comma, 1. I get a slope of about 10.3 and a y-intercept of about 1.4. But from these numbers, it's hard to tell whether that's actually a good fit to the data. Let's plot this line on top of our original data to get a better feeling of what's going on. First, I'll need to generate some data to describe the curve fit. I'll create a new set of x values with a much smaller spacing by typing x underscore fit equals 0. I'll increment by 0.01, and I'll go up to 1. Now I can evaluate the polynomial at these points with the polyval command by typing y underscore 1, those will contain my data points, equals polyval of coefs underscore 1, comma, x underscore fit. Now I'll hold the figure by typing hold on and adding the new line to the figure by typing plot of x underscore fit, comma, y underscore 1. The linear curve fit actually looks pretty reasonable. Unfortunately, pretty reasonable isn't a very good engineering term. We'd like to have a number that helps us decide whether our curve fit is appropriate. As I mentioned in the demonstration, one area of concern when fitting lines to data is how well the line represents the data. The quality of the agreement between the data and the line is often quantified by the correlation coefficient, also sometimes just referred to as R, since R is the variable almost invariably used to represent the correlation coefficient. R is a number between 0 and 1. A low value of R implies that the curve doesn't represent the information in the data well, while a high value of R means that the curve agrees well with the data. An R of 1 implies perfect agreement between the data and the curve, at least at the data points. The Matlab command used to calculate a correlation coefficient is CORR-COEF. I'll do a demonstration of the use of this command next. As I said before, the straight line approximation to the data looks pretty good, but the correlation coefficient gives a more rigorous idea as to how appropriate the curve fit is. In order to use Matlab's CORR-COEF command, I first need to create a vector that's the same size as the original y vector, but based on the polynomial coefficients and the x values of the original data. To create the appropriate data, type y underscore core equals polyval of coefs underscore 1, comma x. Now to get the correlation coefficient, type R equals, so R is the variable name that I'm going to assign my correlation coefficient to, CORR COEF of Y, the actual data, comma, Y underscore core, which is the data generated from the curve fit. The correlation coefficient is about 0.95, which is pretty good since it's close to 1. It's often relatively easy to run a test on a system and measure its response. However, trying to use test data directly to mathematically analyze a system is really difficult. Since using mathematics to describe the way engineering systems behave is one of an engineer's primary tasks, we often find ourselves in the position of trying to determine a mathematical expression that describes the data that we measured. This tutorial covered linear regression, which is one common approach for creating a mathematical expression to describe the behavior of a set of data. I emphasized using Matlab to perform linear regression with the Polyfit command. We also used Matlab's corrcoef command to get a correlation coefficient, which is one way to quantify how well our mathematical expression describes the data. Now, the basic Matlab package only provides the ability to fit polynomials to data. There are ways in which you can use this tool to fit other types of curves, such as exponentials, to data by doing some mathematical tricks with the data before sending the data to the Polyfit command. Now, if this approach doesn't meet your needs, Matlab also has a curve fitting toolbox or add-on supplement to the basic Matlab package. The curve fitting toolbox provides a huge range of capabilities for fitting curves to data.